Oh, crap!
I love it.
All right, good video. Computing is copying and changing. That's something you do to information. And electronic computers are defined by their architecture, and we don't care if you're interested in this. That's it, right? I nailed it. Right? We don't give a... Right? Because that's got to be the attitude, because they're not going to be interested in this. I'm not begging you. I'm not begging you to be interested in copy changey. This is for us, not you. Don't watch the video. Listen, you probably think that computing is something that's done by electronic computers. Wrong. You probably think that a computer is an electronic device. That's wrong. That is not low enough. You have not gone
to first principles, right?
So how do you, not how, we already told you how. What happens when you go to first principles on this? Well, we made an attempt. This is our attempt. But I'm going to tell you, it gets kind of abstract. Don't look at the slide. Listen to me, okay? This is going to get a bit abstract and a bit loosey-goosey. But you have to start. They have to start with that grainy image. Remember the other video? Did you watch?
Yeah.
Did you watch the approach video? You didn't watch it? You don't stop.
How we roll.
Pause it. Open a new tab. Don't close this tab. Open a new tab. Watch the how we roll. Okay.
Okay, go.
This is the first grainy. We worked really hard. Like we had arguments about this. And it was like long and drawn out too. It was a lot of like that sort of stuff. What is computing? What is a computer? It's really hard. Like you look for definitions, they're all inadequate. Computing, don't laugh at me. Computing is copying and changing. Right? Copying and changing is something that you do to something. You do it to information. Mm-hmm. And information is a sticky subject because it's like, it's not data, it's not, symbols, it's not...
it's kind of like all those things, but other things too. It's
an abstraction. It's a concept. Don't worry about that. We'll go into that later. But just think of it for now as copying and changing is done to information. Okay, so when you copy information and change it into new information, you're doing computing. You don't need an electronic computer to do this. You could do it with a bunch of people in a football stadium if they would all agree to work together.
Sure.
A bit is an abstract concept. Everything in a computer can be abstracted away from the electronic level, and that means that computing is not essentially an electronic activity. In fact, their first computers, I think, were definitely not electronic. They're mechanical.
Actually,
go watch the imitation game. Okay. Examples. So copy stuff is stuff like in a modern computer that you're thinking of, it's like the RAM. Just think of RAM it holds copies, but it doesn't.
The CPU is where all the changing stuff
CPU does the changing. Now, if you know something about computer architecture or the parts of a computer, you know that in order to make a copy in RAM, you need the CPU. We get it. Stop acting like you know everything. Okay, we're just trying to get something across here. Other copier stuff is like human memory.
Yeah.
I don't need to explain that. You have one.
Yeah.
Human thinking. That's a changey thing. Yeah. You're not like making a copy. You're playing with the copy, changing it into a new thing. And then finally, the act of writing 5 + 5 = 10. If you write that down with a pencil.
From memory,
you're copying it from here to here. Okay, that's a copying thing. That's a copy activity. But if you see 10 objects and you have to count them and then write down the number 10, that's a changey thing. You're changing this information, the visual image of 10 objects that you don't know are 10 yet, by counting them into the symbol that we recognize as representing 10 things.
Yeah.
Okay. Stay with us.
We can move on to the next one.
Okay, this is the orange one. Just pause it if you're interested, but
don't.
This
is good. No, this is good.
I don't know if they want to hear about this. No.
Well,
all right. Now, so examples. All right.
We had a big argument about this. But we got there.
I mean, this is right. So we tried to construct a simple computer. Mm-hmm. I mean, like,
and I want to let them know what we were referencing to do this.
Okay.
Yeah. We're trying to work out how on earth the computer works.
Yeah, we're not just sitting around thinking about it. We're reading books.
We got a bunch of books. Okay. This one, really good. J. Clark Scott. But how do it know? This is great. So we had this open. We had Charles Petzold, his Code. Really good. Inside the Machine, Stokes. Elements of Computing Systems, Nissan and Shokin.
Building a computer from scratch is the point of that book.
Yep.
We're working on it. We tried to kind of imagine how the logic gates would take input electron patterns like this, governed by the ticking of a clock over time. The patterns don't exist without time. I mean, you can arrange them in a static pattern that's timeless, but that's not what computer programs are. And then the output is a different pattern. Don't worry about this. The point is that we made our first attempt at trying to construct the simplest computer we could imagine. We didn't really succeed, but we have a much better understanding of what sort of things we need to know to succeed. Once you can construct the simplest version of something, you've gone from 0 to 1, Peter Thiel. You've gone from 0 to 1, and then you're just going from 1 to n after that. It's much easier to go from 1 to n. It's hard to go from 0 to 1. I'm trying to go 0 to 1 here.
Okay, and then we took it one step further. You want to...
Oh, yeah. So then we got into the idea, like we're trying to architect a computer, and we didn't realize that you needed to know how to do that before you did it. So we started looking into how to architect a computer. And architecture is where this leads. Basically, how the components are put together in a computer defines what kind of computer it is and how it works, and also how well it can do things in certain contexts. So when you're talking about architecture, you can focus on two architectures. There might be others, but these are the main two that you would talk about in the beginning. Von Neumann architecture, which is most of the computers you would have used, and then Harvard architecture, or really modified Harvard architecture. Mm-hmm. The essential difference between the two is that there's no bottleneck in communication between some of the components within the computer. There's no bottleneck in the Harvard, whereas there is a bottleneck in the von Neumann architecture, and so that's...
So why don't they just use the Harvard all the time?
Well, they use the modified Harvard when they use Harvard. Well, I think it's like algorithms. In theory, there's like a hard mathematical way of defining how efficient it is, but in practice, to actually build it to be more efficient than the nominally less efficient version is hard, or at least it's been historically hard. So yeah. But we don't care if you care about this. I forgot to keep mentioning that. Like, we don't get this.
No,
we kind of do.
We get it enough to.
The hard thing is the first principles thing. Like, how do you stop talking about an input device, a control unit, a memory unit? Like, these things are just materials and electrons.
Yeah, it's just like electricity and like metals.
Metals and chemical compounds and how do you... Well, you're not talking about that when you're using these higher level ideas. Arithmetic and logic unit.
We'll get there.
Units. It's just made of units. That's all it is. It's a central processing unit composed of a control and arithmetic and logic unit.
I think it's like these logic gates just arranged in different ways.
Deep down, I think it's that. So wouldn't it be good to build a NAND gate?
Funny you should say that.
Stay tuned. All right.
Goodbye.
Goodbye. Check out all of our stuff on Patreon. Go give us $8 or $5 or $2, or if you can't afford it, don't worry about it. But if you can afford it, worry about it. $8 gets you everything. Don't you want to be on the phone with us and a group of other people?
It'll be fun. It'll be fun.